Okay, so there are these links I've given. These two links here are just some practice kind of matching graphs. It's an app that lets you match graphs together. So I want you to pause this video and I want you to do these two uh, matching graph activities first. Okay, so just get the sense of how can I visually recognize the different pieces that allow me to match a function with its derivative or even vice versa. Okay, so please pause this video and then do this practice and then come back to the video. So these ones here, so again, I'm going to look at the three main ideas here that we've been looking at. We're looking for where a graph has zero slope. Okay, we're looking for where the graphs are positive and negative, and where we can, we want to see if we can use a polynomial power relationship. So we have here that our x value or slope values are 0. So I'm looking at example 1. So that's the first thing I'm going to look for. I'm going to look for horizontal tangent lines. So one right there, one right there, and one right there. Okay, so what I'm going to do is relate those to 0 coordinates on my f prime graph. Okay, so there's one here, and we'll just say one right about there. So those 0 slope coordinates relate to 0 points on the derivative. Where I want to see next is I'm going to look for negative slopes. So here is negative slopes going to 0. Okay, it kind of starts negative and flattens out. So it's kind of go up and hit that 0 there. I have negative slopes between here and here. Okay, so it's getting kind of going negative, a little bit more negative, and then it comes back to 0. So between here and here, it's going to kind of go like this. Okay, it doesn't get very negative slope, but it does have negative slope. So this one here, notice I've made it a little bit steeper. Okay, that at this point, I'm not too concerned whether you're identifying the steepness or not, just more whether it's positive or negative. So the positive slope parts are here. Okay, so I have positive slope going on, and it's going from flat, kind of steep, to back flat. So it's going from like this and back to there. And there is actually a point where it's the steepest. That means we should have the highest slope. So if that's the steepest, I should maybe move that over a bit. That's the steepest. Okay, that steepest point should really actually relate to the highest point on the slope graph. Because remember, this is y prime. And again, this is going to be positive slope. It's going to be going like that. And so our graph is going to kind of look like that. So that's not a very nice looking graph, but basically the graph's going to go up like that and go through the zeros to those points. So for the next one here, same thing. I want to identify those three pieces. Okay, I want to find 0 slopes where the tangents are 0. I'm going to relate that to a 0 coordinate on the x-axis. So that's about 2.5, so somewhere around there. Okay, where the slopes are positive and negative. So I'm going to start with a negative slope. This is negative, so it starts off kind of steep and flattens out. So it's going to start off kind of very negative and go towards 0 like that. Okay, I got negative slopes in here, kind of starts off near 0, kind of flat, and then more steep. It's going to start up at 0 and just get more steep. And in between, we have slopes that are positive. Okay, so it's going to look like that. So it's going to start off at 0, get really steep, go back down to 0. So it's going to go up and back down like that. Okay, now this is, I should kind of smooth this out a little bit, but basically this is like a cubic function going to a quadratic function. And where it's the steepest, we probably should relate to the maximum slope. So I'm just going to straighten this out a little bit to make it a little bit more smooth because we like our graphs smooth. There it is. Okay, so those are how we can look for how we can map a function onto a derivative function. Okay, so there's some apps that do this. I think I've showed you some apps as well that do this, so that do a much better job than I did here. But essentially, these are things that we're looking for if we're going to do this by hand. So again, some points to observe. Okay, the three main points: horizontal tangents. Okay, so things I'm just going to do this in red here, are horizontal tangents. Okay, where we have horizontal tangents, there, and there, we relate to 0 points on our derivative graph. Okay, where we have positive slope and negative slope, we want to relate to that. So positive slope is in the positive y-axis, negative slope is underneath the x-axis here. Positive slope, again, we're above the y-axis. Notice that as we increase, our slopes are increasing here as it's getting steeper. Okay, the last thing is the power rule relationship. So if it looks like a 1, 2, 3, 4th degree polynomial, which this is not a polynomial, we should have a 1, 2, 3rd degree looking derivative. Okay, so that's an additional part that now we're adding on that we can look at. Okay, so these are things that we're looking for. This one here, I want you to practice drawing these derivative functions by just dragging the point, and we can change the function up, and we can see how the derivative function changes, and we can plot the derivative function. Again, the pieces that we're looking for are where the slopes are 0, relating to 0 coordinates on the f prime graph. Okay, where the slopes are positive, it's going up in the positive x above the x-axis and below the x-axis for negative slope. And the additional piece I want you to start thinking and looking for is the slope increasing or decreasing? That means that whether this is going faster up or more down. Okay, it can still be positive, but the slope is getting less positive, which means that it would be going down like that. Okay, so that's kind of, if you're feeling fairly confident with this, that's the next phase and next kind of layer we want to get to. Okay, so again, we want to try to sketch a derivative from these functions. Okay, so we have the derivative, the function, and we're going to try to sketch its derivative. So for example 3 here, 3a, this looks like a cubic function, so I should be thinking, I'm probably going to get a quadratic looking graph. I want to find the 0 slopes here and here, and I want to locate my 0 y coordinates here and here. That's important. I know it's positive through here, so I should be above the x-axis. Okay, through here. It's going to go up and back down. Okay, so it's going to go 0 steep back to 0. And then I'm going to have negative parts here and here. Okay, so that means that I should have negative graphs going to 0, negative going to 0, and I have a quadratic looking function from that cubic function. Okay, so what about for b? Well, these are discrete slopes. These slopes are not changing. So what do these slopes look like? Well, this section here is a positive slope, and that slope is undefined on those endpoints because remember that we can't differentiate those corners like that. The next section here, we have a constant negative slope. So I'm going to be down here, and it's probably about equivalent, it looks like. So I'm going to be about the same distance down I was up to that point, and then that last point here, again, is discrete. I have to jump right away to a different slope. That point there is, it looks like the slope of the two green lines are the same, so I'm going to keep the heights of those slope graphs about the same. So the slope graph's going to look something like that. Okay. So for this one here, again, we want to try to find 0 slopes. Okay, 0 slope there. It's going to cross x-axis here. I've got negative slopes and I've got positive slopes. So here's my negative slope section. Okay, so it should be entirely below, but it looks like I'm going to be near flat, and then it's going to come back to 0. Okay, so it's 0, gets a little bit more negative, and then comes back up. Here I have positive slope, so it's kind of go from 0 slope to kind of more positive back to 0. So it's going to go 0 slope, more positive, and then it's going to come back to 0 slope. So my slope of that graph should look something like that. Sorry, the slope function should look something like that. Here I can maybe apply that idea that this is a 4th degree looking function, and I want to see if I can draw something that's probably going to look like a third degree function. So I've got 3 horizontal tangents here, here, and here. So I'm going to start with those points. Okay, I'm going to start with my positive slope pieces here. So it looks like it's positive going to 0. I'm going to have negative in between here. So it's negative in there. So it's going to go down and back up to 0. Okay, it's going to be flat and then steep negative, flat. I'm going to have the same thing happening here, but it's going to go 0, steep, positive, flat. Okay, so I'm going to have probably a symmetrical looking piece there above the x-axis. And then lastly, I'm going to have this piece going negative, and it's going to look like that, but it's going the other way, and there's my slope function. And I end up with a 4th degree polynomial looking like a 3rd degree polynomial function. Okay, so the main ideas again are these, right? We're looking for where the slopes are, where is it here? Where the slopes are horizontal or 0, where the slopes are positive, negative, the power rule relationship, and in addition to that, we can start looking for where are these slopes increasing or decreasing. Okay, that's a little bit harder to wrap your head around, but as we get more practice, we start seeing these a little bit better. But again, it takes practice. So I want you guys to make sure that you're doing those matching exercises and looking for those parts, sketching the graphs. Okay, use those apps that sketch the graphs for you so you can see how does a derivative trace out given the different parts of the function. Okay. Okay, so last thing is, what are some conditions that needed for a function to be differentiable? Well, what happened here when we had a corner? It is not differentiable. Okay, so differentiability is based on smoothness and also continuity. So we need smooth and continuous.